Yeah, it's your boy Chill here. Welcome back to Hardware 3D. Today, got a little treat for you. A nice, light, quick video. And we're gonna do a bunch of stuff, but the main highlights are we're gonna look at how we can save our render target. We can save those contents to an image file. It's gonna be useful for some debugging stuff. And I'm gonna teach you guys a little bit about input layout that you might not be aware of. This is a little thing that came up for me, and I learned something new. It's a today I learned kind of situation. So that's going to be interesting. And also I'm going to show you a little trick that you can do with the compiler to get some very useful warnings about virtual destructors. All right, so let's take a look at the commits here. The first one, we re-add the ability to, change the blur kernel at runtime. It's not that big of a deal. We just add function to render those controls. We add that to the render graph. And we add a function to set the kernel as a box. So we're going to have the option to have Gaussian blur or box filter blur. And then down here, it's just, most of this is just ImGUI code. Render a combo box, a couple of sliders, and stuff to reset those the kernel. In app.cpp here, we're just going to now call render widgets. That's going to put that on the screen. All will be good in the world. Next thing I do here, not a very big deal. I just add the Goblet model and the Nano model to our Sponza scene. And so here we are. We're in Sponza. We've got the Nano. We've got the Gobbler. Everything, it's all good, right? Now, here's one thing that I want you guys to notice. So look at the camera here. And notice the yaw. Notice how it's like wigging out and it's in a bunch of it's weird angles, like 530 degrees. Yeah, so I fixed the clamping code, but I didn't fix it correctly. You can see here, fix wrap angle. Again, I was missing a minus, so I just added a minus in here, and now that works properly. We got to come in here to delete some files that weren't being used. And here, I do a neat little thing. So ImGUI, it remembers the positions of the windows and, their state, whether they're minimized or whatnot. So next time you open the program, it's going to have those same positions. Now, I don't commit that INI file. So when you clone this project for the first time and you open it, the windows are all going to be in weird positions, and then you have to reposition them. So what I've done here is I've added a default ImGUI. And in the ImGUI manager here, when you open it up, it checks to see if the INI file exists. And if it doesn't exist, but we have a default, then we just copy that default to imgui.ini. So now if you clone the project fresh, the windows will all be in a sort of sane starting location. The next commit here is a little bit of organization. What I'm doing is I'm just moving the shaders into their own folder because I got sick and tired of them, chilling out in the same folder as my source files. So I created a shader bins folder, and if you look at the VC project, now all the output for these shaders, it's going to output to shader bins. Here's another weird feature I added to the code. So in the script commander, I add a new command called publish. It's got a helper function there. Here's the publish command. You can publish to a destination. What that does is, if you want to give this program to someone, you can't just copy the exe to them, right? You got to give them the exe, you got to give them the shaders, you've got to give them the DLLs, you've got to give them, perhaps also models that they might require. And it's annoying to do that. So what I've done is I've created this publish function, and all it's going to do is copy all the things that are required into the destination folder that you supply. So it makes it easy to, create a simple folder of everything that someone would need if they want to run the program. And you can just zip that up and send them to them. So if you wanted to do that, you would, go into process.json, you would enable it, set this to true, and you'd have a command in there, publish, and you'd have a destination folder, and all would be good. And finally here, we finally transition the code base to Visual Studio 2019. So for those of you who, have been checking the code out regularly, cloning it or whatever, if you're on Visual Studio 19, now you won't have to retarget. And now the videos too will all be using Visual Studio 2019 now. Here I just changed the starting position of the camera because it was in a weird space for whatever reason. So instead of hard coding, it's, default position into this function here, I have home position, home pitch, home yaw, which can be taken into the constructor, and they'll just be stored, in the class here. Added a utility function to check to see if a string contains another string. So split string, this was added when I did the render graph stuff. I don't think I actually went over it, but it's not that complicated. It's very simple. Very simple standard library stuff. String contains just is a wrapper around std search, and check to see if it returned an iterator to the end. If not, then the string contains the substring. Okay, now we got something interesting here. So for the render target, at the beginning of the video I mentioned this, but I had need of the ability to save the contents of a render target as a file. Now we already have the saving, we can already save an image from Surface. So for me, it was the best just to create a function that would convert render target to a surface. So this is a fairly basic but still interesting task to achieve in Direct 3D. The meat of what we want to do here is we want to get the texture for that render target, and we would like to, map it, get a pointer, and then we can copy those bytes from the GPU side into our own surface. Seems simple enough, except that in general, the surfaces that you create on the GPU, the textures, the shader resources, we don't generally create them with the ability to be read from the CPU, because that puts restrictions on them that can make your engine run slower. So then how do we read from them? Well, we can create a staging texture, which is a texture that can be read from the CPU. Then we can use the GPU to copy from the original texture to the staging one, and then we can map the staging texture and copy that. So first thing we got to do is, what we have is a pointer to a shader resource view, but we want the resource. So easy enough, we call the function getResource, and that'll give us an ID3D11 resource. Now we don't actually want the interface of a generic resource, we want a specific interface of a 2D texture. So we've got a query interface, and comPointer gives us a very nice function to query interface called as. So we would do pointer to the resource as texture, and we just have a comPointer for ID3D11 2D texture. So then we have this texture. What do we want to do? Well, we want to create another texture that is compatible with our original texture, but that allows CPU access. So what we're going to do is we're going to get the descriptor from the original texture. We're going to fill that into this structure here. Now we have that descriptor. We got to change a few things. We got to add CPU read access. We got to add its usage as a staging texture. And bind flags is 0 because we're not using this to bind to the pipeline. We're only using it as a staging texture. Once we got that, we just create texture 2D. We use that to fill this interface. That is a pointer to our temporary texture, our staging texture. Once we've got that, then we can call copy resource, which is a GPU command. So we get it from the context, and this allows us to copy from one texture to another. Well, from this one to this one. The order is backwards, doesn't matter. So now we have this texture and we are able to access from the CPU. So let's create a surface on the CPU side. We'll create its width and height are going to be the width and the height of this, this render target. And then we're going to call map on this texture here. And again, you got to use the context for that. We're mapping this thing for reading, and the information is going to be stored in this structure here. The important part of that information is the pointer to the actual data. That is the pointer that is going to be mapping into GPU memory, and the distance in bytes between rows of that data, that image data. And then all we do is we do a 2D loop through Y and X, looping through those bytes, and we dereference them. And then we call putPixel to copy those values into our surface. And when we're done, we got to unmap that memory on the GPU. And then we're done. We just return our surface. We'll get our copy elision, and we'll have our surface. And of course, because we're using smart pointers, all the resources that we created here and all the different handles, they're all just freed automatically. You don't have to worry about them. All right, now what I do is I use that ability to debug a problem in a separate project that I'm working on with the same similar code base. I ran into a very nasty bug, and it took me a while to figure it out. And the ability to save my render target was part of what enabled me to debug my problem, narrow down exactly where the issue was. But I am in this video here. I'm going to show you the gist of what the issue was. So I created a couple of vertex shaders and a pixel shader. The pixel shader is very simple. It gets in a color and it returns that color. Just very simple pixel shader. The vertex shaders here, we have one vertex shader. It accepts position and color. And the second vertex shader here accepts only position. So this one outputs a constant color, which is green. This one outputs the color that it was given from the vertex data. So I write a simple test. What do I call it here? D3D test scratchpad. So it's a simple function here that I was using as a scratchpad for D3D tests. And inside this function, I create a lambda function, render with vertex shader, and it takes the name of the vertex shader in. So what does it do? Well, it's going to create a whole bunch of all the bindables that you need to do rendering. So you got your topology of triangle list, got a vertex layout, vertex buffer, index buffer, pixel shader, which is common for both cases, is going to be test PS. Vertex shader, which is going to be loaded based on the name that was passed in to this lambda function, and input layout. Finally, we have the render target that is used for this. And then once we have all these pieces, we bind it all, we draw, we restore the swap buffer as the render target just to keep things clean. And finally, the off-screen render target that we were rendering to, we convert that to a surface and we save it to a file called test_name of the vertex shader. And then here you can see I'm calling this with test1 VS and test2 VS. So far so good. And what we should expect is after running this, we should expect to see two PNG files appear in our working directory. And if we look at this geometry, we can see, okay, I mean, it's a triangle, right? It's a triangle. Every vertex has a position and a color. And if we remember from these shaders, we should expect one of the images to have a green triangle, and the other image should have a triangle that has, every vertex has a different color and they're blended. So we don't see any PNG files with test in their name. Let's debug this bad boy. We're going to put a breakpoint on D3D test scratchpad. Here we are. Let's step in and we'll step into this bad boy, render with vertex shader, test1. And we create all the different bindables and the buffers, everything. We bind them all to the pipeline, clear the render target, bind the off-screen render target, draw, and finally we're going to save that to a file. And if I look in here, we've got test_test1vs.cso.png. And if we open that up, yeah. So this is the one where we're using the per vertex color data, and it looks perfect, looks fine. Now if we step over this other lambda call and we look in here, we got another one and it's all green, which is what you would expect from that shader code, from the vertex shader code. So no problem, everything is working fine. Okay, now note that these two are, completely independent. They work independently of each other. They don't share resources or calls in here. Let's put them in the opposite order and see what happens. All right, render with vertex shader, test2, step over, no problem. Test1, exception. Oh, really? So we switched the order and now we get an exception. And if we look at, the data that's contained in that, we see it says input assembler, vertex shader linkage error, signatures between stages are incompatible. The input stage requires semantic index color as input, but is not provided by the output stage. Now what this is saying, basically, is that our input layout isn't providing the color. It's only providing the position. But if we look at our input layout that we're creating, we see, no, it has position and it has color. And you might think, well, maybe there's something wrong with the thing that builds our, vertex layout. But trust me, I debugged all that code. There was no problem. It was the exact one that you would expect. And furthermore, it's weird when you try to draw them in the other order, it works fine. But here's the thing. If you do more testing, like I did, perhaps many hours of testing, you'll realize it's not the order in which you draw them that matters. It's the order in which they are created. So if you create the stuff from test 1 first, then everything works fine. But if you create the stuff from test 1 second, everything blows up. Now, it was quite a journey to, narrow down all the possibilities and run all the tests and figure out exactly what the problem was. And I'm not going to go through all that here because that would probably take an hour to take you through that whole entire journey. So let me just hit you with the summary, with the important facts here. It doesn't make sense to me that it's telling me there is no color when my input layout definitely has a color and my vertex buffer definitely has, color components in it. Here's the thing. What I thought was that every, Direct3D input layout, every Direct3D, the same layout, they're all the same. So if I have one layout that was created with the position 2D and a 3-component color component, that would be, usable in any place where I had that set up for vertex buffer. But that's not true. So when you create a Direct3D input layout, you have to pass in the bytecode from a vertex shader. And the actual input layout object is a combination of information from the shader and the vertex layout descriptor that you provided. That array that tells you every element in the vertex buffer. Those two things combined make the input layout. So the same layout with a different shader that has a different signature might not be compatible, but sometimes it is. So let's take a look at those shaders again. Test 1, the input signature has position and color. Test 2 only has position. So test 2 is a subset of test 1. And what I've found this means is that when I create an input layout, I give it an array of elements that has position and color. If I create that with test 1, it will create an input layout that contains position and color, and it'll work with this shader and with this shader. But if I create an input layout with the same array that has position and color, but I use the shader code from this shader, the signature only has position. So what it will do is it will create an input layout that ignores the color because it looks at the shader and it says you don't need that color. We can ignore it. Now the final piece of the puzzle here is our bindable codecs that allows us to reuse Direct3D resources. So for the input layout, the way I determine whether an input layout is identical or not is via the layout. Because I assumed that two inputs with the exact same layout, if two inputs had the layout of position and color, then they could be used interchangeably. But that's not the case. So what happens here is when I call this one first, it is going to create an input layout with this layout, this element array, and this shader. And that's going to be inserted into the codecs. And then when I call this one, it's going to try to resolve one out with this layout, but it's going to see, oh, there's already one in there with that layout. It's going to use the layout that was created here, but the one created here was created with this shader, and so it's going to ignore the color, and that's why you get that error. So it was a little surprising for me that input layouts created with the exact same layout structure aren't actually the same. But it makes sense here because you are passing in the bytecode. So there is a kind of, overlap between those. And the way I've solved the problem, at least temporarily, is in input layout now. Instead of just taking the shader bytecode, it takes in a vertex shader object. And now the unique ID of the input layout is not only the signature of the layout, but it is also the name of the shader. So now two input layouts with the exact same layout array, but that have been created with different shaders will not resolve to the same instance. You can see before, the UID was just the name of the input layout class plus the code for the layout. And to that, we've added the UID of the vertex shader. Now, in reality, you could have different shaders that share the same layout if they had the same signature, or at least compatible signatures. But in order to do that, cleanly, we'd have to have shader reflection, which we don't have in this system yet. But if we add shader reflection, we might be able to make it so that input layouts can be shared a little more effectively. So yeah, that was a little bit of surprising information for me. Definitely good to know. It definitely was very difficult to debug in a large project where you don't even know what the problem is. But when you change something, when you click somewhere, it just crashes. The final thing we're going to talk about today is another bug I had in a different project that I'm working on with the same sort of code. And the cause of the problem when I dug into it was that I was missing a virtual destructor on some of my base classes. And this is a thing I do fairly regularly. And if I'm being honest with myself, I'm probably going to be doing it, in the future, no matter how many times I tell myself, don't do that. So I looked into it and I figured there's got to be why doesn't the compiler issue a warning for this? And so I looked into it, and there is a warning for that sort of thing. You won't find it in the general user interface here, but you can add a command line switch when the IDE executes the compiler. And the warning number is, level 3, 4265. And this warning generally tells you when it thinks that you need a virtual destructor somewhere, but you don't have one. I found it isn't perfect. It doesn't tell you the exact place, but it alerts you to the problem so that you can figure out what you need to do. Now, the main problem with enabling this warning is that there are some coding paradigms in C++ where you have inheritance, but you don't have a virtual destructor, and that is by intention. You generally see that in the mix-in pattern. So it just so happens that WRL.h uses that design pattern quite a lot. So when you enable that warning, you see a butt ton of warnings come up. So let me show you what I mean. I'm going to remove these pragmas here that disable that warning temporarily, and I'm going to compile. And you see the program compiles and runs fine. But if we look at the build output here, we see, there's a little bit of spam. There's a little bit of warning spam here. And you can see it's all from WRL. So obviously doing this, it's not going to help you. You're not going to be able to find actual warnings in between all this spam. But the solution is fairly simple. I create my own wrapper header around WRL. And I just disable and then re-enable that warning between the inclusion of WRL. And then I just include chili WRL everywhere I was including WRL.h in the first place. And if I build this, you see here, it does indeed catch a case where I had virtual functions, but the destructor is not virtual. It's MP, which inherits from model probe, which tells us that model probe probably needs a virtual destructor. And if you look at this commit here, you see, yep, model probe added a virtual destructor there. Also added one to technique probe. So it's just a little compiler setting that I think is worthwhile to enable. But there you have it. And just some general improvements and fixes to the engine. And we learned a lesson or two along the way. In the next video, got two things on the docket. Number one is I want to add the ability to have multiple cameras in a scene and to be able to switch between them. And number two is I want to be able to visualize the view frustum of a camera in the scene by rendering it with wireframe rendering. So we're going to learn how to do wireframe rendering. We're going to have visualization for multiple cameras, and that is going to tie in a little bit to our overall goal of implementing dynamic shadows. Until then, thanks for watching. Hope you enjoyed this video. If you did, please click the like button, helps a lot. And I will see you soon with some more Hardware 3D.